We can also reproduce the plot from the previous session by using this formula here, this function. We're defining a warping phase function. It takes as an argument an input vector of normalized frequencies and all pass coefficients, and will return this warping phase. So here we see this is the same equation that we found in the Oppenheim book, Discrete Time Signal Processing. So we see that for A equals to 0.5, that's the blue curve, we observe a stretching of the low frequency range, where a small part of the low frequencies stretch over a wider phase range than the other curves. So when we take a look here again at this plot, here we see the blue curve here, that's the curve from A equals to 0.5, and we note there is a stretching of the low frequency range. So where the low frequency range is here, and we see stretching of the low frequency range, where a small part of the low frequency stretch over a wider phase range than the other curves. So when we compare with the other curves, we see this stretching. Yeah. So this is another way to have the same plot. That time we used SymPy to obtain this plot. So we didn't use the equation given by this book. We went from this equation, we calculated the magnitude, we calculated this phase using these formulas here, using SymPy, and we had this plot. At this time we are defining this warping phase, when we are defining this equation of the phase here, and we are having the same plot. Yeah? The phase at the output of our phase function can be also interpreted as a normalized frequency. This means its output can be the input of another warping phase function. So an interesting observation is that the warping phase function with coefficients minus complex conjugate A is the inverse of the warping phase function with the coefficient A. So how can we observe that the warping phase function with the coefficient minus conjugate A is the inverse of the warping phase function with coefficients A? We can use Python. So here, this is the Python code. Here importing matplotlib to plot. So here we define a range of frequencies from 0 to pi in steps of 0.01. So here is A is equal to 0.5 times 1 plus j, and then we are having here, we are calling our warping phase of the warping phase with omega na and the minus a conjugate. So if we remember, the warping phase takes frequencies, an input vector of normalized frequencies, and the all-pass coefficients. So all-pass coefficients now is the minus a conjugate, and the frequencies is the warping phase of A. Then we have here, we see that indeed this is the identity function, and this shows that interpreting the all-pass as a normalized frequency warper, the all-pass with coefficients A is inverse to the all-pass with minus conjugate A.